Hello, everyone. Today, I will talk to you about Bayes' theorem. Now, Bayes' theorem is an incredibly important part of probability theory, and it has many applications throughout science and engineering. And furthermore, it can help us reason with evidence in our everyday lives. So today, what I will do is introduce to you the basic idea or how Bayes' theorem works, and we'll also see how to apply it to a couple examples. And I will note that moving forward, so on the problem set this week, as well as what we'll be doing next week, and also on the final, there will be questions involving Bayes' theorem. So this is one of the most crucial things I want you to take away from this unit on probability theory. And so it's very important that you understand what Bayes' theorem is and how to apply it to answer certain questions. And furthermore, learning this skill will help you beyond this course, but also in other parts of your academic journey and maybe even your life. So what I will do is I will begin with a famous example. And this famous example has to do with the kind of cognitive illusions or systematic mistakes which people make when reasoning with probabilities. And we'll see how using Bayes' theorem actually clears the air with regard to this confusion or this mistake. So we'll work through a very famous example, and Bayes' theorem will help shed light on how that example works. And then so after we've seen Bayes' theorem in action, we'll then talk in general about what it is, and then we'll return to another example involving Bayes' theorem and then talk in general about what Bayes' theorem is telling us about these two examples. And that final thing, that illusion, has been called the base rate fallacy. So let us begin with our famous example. So I want you to imagine that you hear on the news, say that in New Brunswick, New Jersey, that a cab was involved in a hit and run accident last night. That is, a cab hit a pedestrian and then didn't stick around to, for instance, get in trouble, but just drove off. So now I want you to further suppose that there are only two cab companies in the city. There is the green cab company with green cabs, and there is the blue cab company, which has blue cabs. Now, suppose further you're given the following information. You know that 85% of the cabs in the city are the green ones, and 15% are blue. So that is the grand majority of the cabs that are roaming the streets of New Brunswick are green, and a small percent, 15%, the rest are blue. So again, you know that there's many more green cabs than blue cabs. But in addition, there was a witness who was at the scene. And the witness says that the cab they saw was blue. Now, the court tested the reliability of this witness under the same circumstances that existed on the night of the car accident, and concluded that the witness correctly identified each one of the two colors 80% of the time and failed 20% of the time. So what in B, we have that the witness did say that the cab was blue, and then upon further investigation of how reliable the witness was, what was determined was that um, if the cab was green, say, in these tests that were testing the reliability of the witness, suppose whenever there was a green cab put in front of the witness in the same circumstances, 80% of the time, the witness said that it was green, and the other 20%, they failed to identify it. They said it was blue. And vice versa, whenever there was a blue cab set up in the same circumstances, the witness, 80% of the time, said that correctly identified the cab as blue, and the other 20% of the time incorrectly said that it was green. So we have that this witness, given that the cab is a certain color, is 80% likely to say that the cab is that color, and 20% likely to incorrectly say that it was that color. So given this information about the cabs in the city and this witness who said that it was blue, and this information about the reliability of the witness, we might ask the following question. What is the probability that the cab involved in the accident was blue rather than green, given that the witness came forward and said it was blue? So we are asking, what is the probability that the cab was blue, conditional on the witness identifying it as blue? That is to say, what is the conditional probability of the cab being blue, given that this witness here says it was? So take a moment to think of what the intuitive answer might be to that, the one which comes to mind. So most people answer this question incorrectly. Most people say that the probability, the conditional probability that the cab is blue, given that the witness said so, is 0.8 or 80%. And that is the reason for that answer is that the witness is 80% reliable. So given that this witness said the cab was blue, and given that the witness is 80% reliable, many people think that therefore the probability that the cab was blue is 80%. But this is incorrect. And we will see in this lecture, given Bayes' theorem, why exactly this is the incorrect response, and why the answer which we immediately jump to of 80% is a kind of cognitive illusion that gets in the way of critical thinking. And now that we understand the rules of probability theory, and especially Bayes' theorem, which you'll understand by the end of this lecture, we can overcome that cognitive illusion and become better critical thinkers. So to find the correct answer, again, what we're being asked is, what is the conditional probability of the cab being blue, which here I have symbolized as blue, given that the witness said it was blue, and here I symbolize that with W subscripted with B. So the witness says it's blue. What is the probability, again, that the cab was blue, given that the witness says it was? And what you have to note is that the question or the problem here, this setup, does not tell us this number directly. We are not told directly here what the probability of blue is, given that the witness said so. Here's what we do know from the example. We do know, among a couple other things, that the probability that the witness will say it's blue, given that it is blue, is 0.8. So the probability, again, that the witness correctly identifies a color is 80%. And that's what the example does tell us about the witness's reliability. But note, crucially, these are two different things. The probability that the cab is blue, given that the witness said so, is different than the probability that the witness says it's blue, given that it is blue. So this incorrect answer is assuming that these two numbers are the same, but that is not an assumption we can make. We have to look at the additional information that the setup or the problem about the cabs gives us. So in addition to it telling us that the probability that the witness will correctly identify it if it's blue, given that it is blue, is 0.8. We also know that the probability that the witness will say it's blue, given that it's not blue, i.e. given that it's green, is 0.2. And we know that because we know that the probability that the witness will say it's green, given that it's green, is also 0.8. And what that means is that, and green here is equivalent to not blue, because we assume that there's only two types of cabs in the city. So the cab has to be either green or blue. So not blue is the same as green, okay? And since we know that the witness is 80% reliable, that means that if the cab is green, i.e. not blue, there's an 80% chance that the witness will say that it's not blue, that it's green, which is to say that there's a 20% chance that if the cab is green, the witness will say that it's blue, will incorrectly identify it. So from the reliability of the witness, we know these two conditional probabilities. But these, so far, don't directly tell us the conditional probability in question, which is the probability that the cab is in fact blue, given that the witness says so. Now, we have to look at this additional information, which is the background distribution of overall cabs in the city. So as I said in the setup, 85% of the cabs in the city are green and 15% are blue. So the unconditional probability, regardless of what the witness says or any other evidence we have, given that we know that 85% of the cabs in the city are green, or i.e. not blue, and therefore that 15%, the rest are blue, we know that the unconditional probability that a blue cab did it is only 15%. That is because there's so many less blue cabs, so there's a small percent chance, unconditional on any evidence that it was a blue cab, because it's more unlikely that it's a blue cab because there's just less blue cabs hanging around, so to speak. And on the flip side, the probability that it wasn't blue, i.e. the probability that it was green, a green cab, is 85%. It's very high because there's a lot of green cabs driving around. So the unconditional probability that it was a green cab is high, it's 85%. And this information here about what we will see, the base rate, or the unconditional distribution of blue versus green cabs, is essential to answering this question. And we have to take it into account in understanding what the probability that it was blue, given that the witness said it was. And we have to take into account these base rates, or the background number of cabs, in addition to the information about the reliability of the witness. So how can we do that? So I want to just simply help ourselves to the following formula. So, and this formula is an instance of Bayes' theorem. And after I work through this example, I'll talk about this formula in general and explain to you how it works and what it means in general. But to answer this question at hand, let us just assume that the following formula works. And what we have is that the probability that it was blue, given that the witness says so, and this is what we're looking for, this equals the probability that it was blue, the unconditional probability that it was blue, times the conditional probability that the witness says it was, given that it is blue, over the unconditional probability that the witness says it's blue. So if you recall the previous slide, what we have directly from the question, you'll notice that we have the numbers to compute the numerator. We already know from the question the unconditional probability that the cab was blue, which did it. And we also know this fact about the witness's reliability of saying that it was blue, if it was blue. But if we look at the denominator, we'll see that we are not given the probability of the witness saying it was blue, the simple unconditional probability. We are not given that directly in the question. So what we have to do is we have to help ourselves to a way of calculating probabilities, which I introduced a couple of days ago on Monday, which is the law of total probability. So we have to unpack the denominator using the law of total probability. So using the law of total probability, what we see is that the unconditional probability that the witness will say it's blue equals the probability that they say it's blue, given that it's blue, times the probability that it's blue, plus the probability that the witness says it's blue, given that it's not blue, times the probability that it's not blue. And here, if you look on the right-hand side of this equation, here we have all of these numbers. This first term that we're summing up is simply the numerator, and the second term we're summing up is given to us as well by the question. And so what we do is we just fill in the numbers according to the question. So the reliability of the witness, and saying that it's blue if it is, and the flip side of the reliability, which is that the probability that the witness will make a mistake, i.e. say that it's blue when it's not, which is 0.2, and you multiply 0.8 and 0.2 by the unconditional probability that it's blue on the one hand and that it's not blue on the other. And what we get by simply doing that math is 0.29. So now let's put this all together. So if we combine our calculation of the denominator with what we know about the antecedent, what we get is 0.15 times 0.8 over 0.29, which is 12 over 29, which is roughly 0.41. So what this tells us is that given our understanding of how many blue versus green cabs there are in this city, and given this evidence of this witness, which we said was 80% reliable, given the evidence of this witness saying it was blue, the probability that the cab was in fact a blue one which committed the crime is just about 41%. Now this is striking because the intuitive answer which many people give is about double that. Many people just simply say that the probability that the cab was blue, given that the witness said so, is 0.8, and that is a lot higher than the actual answer, which is 0.41. It's about double. And the reason why the actual answer is much less than 0.8 is because even though we have a very reliable witness who says it was blue, nonetheless, there are still so little blue cabs compared to green ones in the city. And the fact that there's so little blue cabs compared to green ones, that information has to be taken into account when we think about the probability that it was blue, given the evidence of the witness. And once we take that information into account, what we see is that it balances out the reliability of the witness, so it decreases. So we get something, the answer is much less than simply 0.8. But now we might ask ourselves, where did this formula came from? Where did this key equation come from, which helped us get the right answer? And the answer is that this is Bayes' theorem. And in the next video of this lecture, I will justify Bayes' theorem. And then after doing that, we will return to another similar example as this cab example and talk a bit more about how to apply Bayes' theorem and what it tells us.